Alright, so before we had talked about mechanical energy, and I had told you a few things. One, that it was the ability to do work. Two, that mechanical energy comes in two flavors, kinetic energy and potential energy. That it has units of joules, or in other words, newtons times meters. That it is a scalar quantity. Energy, same as work, is a scalar quantity. And finally, I had said that it is conserved, and there was a little asterisk on that because it's conserved only when using conservative forces. So I wanted to talk just a bit about what exactly that means. Alright, so conservative forces like gravity are path independent. That means if I say take this marker and I lift it up to the same point from starting at A and moving to B in two different ways, one going up like this and one following this path here. As long as I start and end at the same point, the work that is done by gravity is exactly the same, right? Because we had talked about the work done by gravity is going to be just m times g times that change in y, right? And it doesn't depend at all on this path between the two. That's what makes gravity a conservative force. Now let's talk about a non-conservative force. Friction is a good example of a non-conservative force. And what makes it non-conservative is that I can go from point A to point B in two different paths and get two different amounts of work done by the friction force. So let's talk about the friction force from acting on this marker as I move it from point A to point B. Okay, now if I go in a straight line, right, you can even hear friction acting on the marker as I move it, because that's what causes that squeaking noise. So that was the straight path. Let's call that path 1. And now I will take another path that's significantly longer. Okay, so I had path 1 down here, and path 2 goes this way in this arc. Now notice, along both of these curves, friction is always opposing displacement. So for every little displacement element dl, whether it's along here or it's along here, dl and friction are always in opposite directions. Since dl and the friction force are always acting in opposite directions, as I move across, every element dl contributes the same amount, whether I'm going straight across or whether I'm going around in a circle. Because these two things are always at 180 degrees, the displacement element and the friction force are always anti-parallel or anti-aligned, no matter which way I'm going. And that means each dl element contributes the exact same amount. So it's not the case that, when I move up and then when I move down, it contributes differently. No, when I move up, the friction force is pointing down. When I move down, the friction force is pointing up. So the displacement element dot with the friction force is always going to give me this negative contribution. Doesn't matter if I go in this path or that path, every small element will add up. And since there are more elements going this way, because it's a longer path, I end up with a larger amount of work done by friction going up around in this trajectory than I do going straight across. So it is a non-conservative force because it doesn't just depend on the beginning point and the end point, it depends on the particular path taken between those two. Now there is another way to say this, which is that if you start at one point and you go around in a closed loop and end back where you started, if that process of going all the way around in a closed loop and ending up at the same point where you started takes no work to do that, then you have a conservative force. This is the case with gravity, right? If I take something, I pick it up, and then I set it back down in its original location, gravity has done net zero work. In the case of, say, friction, right, there is work done at every element all the way around, and that work never changes sign at all, right? The F dot dl element is always going to be negative. It's negative when I'm going up, it's negative when I'm going back down. Therefore, it does take work to take something and slide it around in a circle. See? If I take this object and I set it here on this surface, and I slide it around in a circle there, I have to put energy into the system at every point as I'm moving it around. So, that makes friction a non-conservative force. There are other examples of non-conservative forces, like, for example, air resistance. All of these path-dependent forces are non-conservative. There's plenty of examples of conservative forces. There would be the electromagnetic force, the gravitational force, and the spring force, as we'll see in this chapter as well. So I'd like to show you a classic example of conservation of energy. If I pick up one of these balls in this Newton's cradle, I can impart to it some gravitational potential energy. If I then let it go, that will be converted to kinetic energy, and then it will be passed on to the other steel balls that it strikes. Now, as these things transfer energy, every time a ball goes up in the air, you're gathering gravitational potential energy and losing kinetic energy, and when the ball falls back down, it's gathering kinetic energy and it's losing gravitational potential energy. Now, over time, this oscillation gets this oscillation tends to go away. And the reason is that this is not a perfect system. There are some non-conservative forces acting on this thing. If there weren't, it would go like that forever. The non-conservative forces involve air resistance. There's also that little bit of energy due to sound that is lost from the system. You could hear that. So that's all that sound energy is mechanical energy that is lost by the system. And also, these are not ideal strings, right? They rub against the sides where they're attached here and here. And that means that there will be some friction between that tension and that, between that string and the bar. And that means that because there's friction acting there, there will be a little bit of energy loss as well. Over time, you'll lose some energy because of those non-conservative forces. But if you use your imagination a little bit, you can imagine what this would look like if there was no energy lost, right? If the oscillation just kept going on forever. And this would be a perfect example of how gravitational potential energy can be converted into kinetic energy, and the entirety of the mechanical energy is conserved over time. Now that we've defined conservative and non-conservative forces, we can talk a bit more about potential energy. So first of all, potential energy is only well defined for conservative forces. So that means you'll see things like gravitational potential energy, you'll see things like elastic potential energy or spring potential energy, but you won't ever see anything like the potential energy due to friction forces or air resistance. That is not a well-defined quantity. So only use potential energy in the case of conservative forces. Remember from last time that the change in potential energy, right, is the work done from an external force in bringing a system from one state to another, from its initial state to its final state. Or in other terms, you could write it as minus the work done by internal forces, negative the work done by the internal forces within the system. Now, let's just use this to calculate elastic potential energy, or the potential energy of a spring. So you can imagine if I have a spring, say, that is sitting here, and it's at equilibrium at x equals 0, then if I take an external force and I stretch it out to some distance x, then I have essentially put some energy into the system, right? It takes energy for me to do this, to stretch the spring out, and I have then given the spring some spring potential energy. It's not moving yet, so I haven't given it any kinetic energy, but I have put some energy in those coils that is there, ready to be converted into kinetic energy if I were to let go. So let's calculate what the elastic potential energy is. Spring potential energy and elastic potential energy are two terms that I'll probably use relatively interchangeably. Technically speaking, elastic potential energy can come from things besides the spring, like say here I have a rubber band. If I stretch it out, I am giving it more elastic potential energy. And I can stretch it out around this, my son's little rubber band shooter here, and gotcha. All right. The change in potential energy then, when I take this spring and I stretch it from its initial position at x equals 0 out to x equals x, is going to be minus the spring force dot dl with the integral from its initial location to its final location. And so the spring force is the internal force, so I'm going to include that minus out there in front. Now notice, right, dl is going that way. The displacement is along the x direction, so it's a dx in that direction. And the spring force is anti-aligned to that, right? The spring force is pointing in the other direction. The displacement goes in that direction. The spring force goes in this direction. So these two things, once I take their dot product, right, they are anti-aligned. So I'm gonna pick up another minus sign. So that means I'm gonna have this is equal to, it'll be a minus an integral from 0 to x. The spring force is minus k times x. The dl is going to be along dx, and that means I have these two canceling each other out. I can then do the integral if I have a little more board space, so let's just move this back over here. This would be then the integral, I can pull k out front because k has no dependence on x. It'll be the integral from 0 to x over x dx. So integral of x is going to be x squared over 2. So I have an x squared over 2 from x to 0, and that's just k x squared over 2. So that is the expression we get for elastic potential energy. Right? U elastic is equal to 1/2 k x squared. So here I wrote down the two different kinds of potential energy that we've talked about so far. We talked about elastic potential energy and about gravitational potential energy for an object which is a distance above the ground. And here is the general definition of potential energy for some force. If I just think about the one-dimensional case here, in one dimension, if I just have a single dimension force, then I could talk about, say, the change in potential energy as the potential energy at some location minus the potential energy, say, at some reference point. It wouldn't really matter. And I could set that equal to minus this integral, right, from the reference point to x of f of x, this one-dimensional force, over x. And I could just take the derivative of both sides of this equation. On the left-hand side, I would have, well, for the first term, I would have du dx. The derivative of this reference, of u reference, which is a constant value, would be 0. Right? And that would be equal to, on the right-hand side, I have minus the derivative of the antiderivative of f. Okay, and the derivative of an integral or an antiderivative is just the function inside of the integral, otherwise known as the integrand. So I have minus and then f of x there. So if I just multiply by minus 1 on both sides, you'll see how force relates to potential energy. Force is equal to minus du dx. All right, so let's go back to talking about conservation of energy for a minute. Now, let's say that we have a system of objects that I've drawn here. They're interacting with one another. There's a spring force, say, between two of them, and let's just say that they all have mass, so there's some gravitational interactions going on between them. And why don't we just throw in, for the sake of argument, that this one has some negative charge and that one's got some positive charge, so there's also an electric field or an electric force happening here. So all of these objects are interacting in some way, and always via conservative forces. Okay, let's consider what happens with this system. Well, as they interact, if they change position, they'll change their potential energy. The total potential energy of the system will change, right? And we know that the change in potential energy is minus the work done by the internal forces. And what about the kinetic energy? Well, we know that the change in kinetic energy is, I'll do KE to be consistent. The change in kinetic energy is equal to, right, the net work done on the system, right, because of the WEP, or the work energy principle. And if we make our system big enough so that all of the forces that are acting on the system are all internal forces, there's no external forces, like there's no applied force pushing this box with these objects over to the side or anything like that. All forces that are relevant are internal to the system. Then that means that the work done by internal forces is just the net work, right? So we would have the change in potential energy would be, right, minus the net work. And so I could just add these two things together, right? Add, we'll call that 1 and we'll call this 2. Add them together, and 1 plus 2 gives you that the change in kinetic energy plus the change in potential energy is equal to 0, which is exactly the statement of conservation of energy, right? So the change in kinetic energy plus the change in potential energy, that would be kinetic energy final minus kinetic energy initial. Or, in other words, adding the K initial and U initial to both sides, right? Kinetic energy final plus U final is equal to kinetic energy initial plus U initial. So that means then that there is no change in the total mechanical energy over time, right? So long as there's no non-conservative forces acting on your system, you will have conservation of energy. Okay, now let's say that we're going to introduce some non-conservative forces. Now, let's just say that maybe we pumped this system full of air, and now there's some air in here, and that means that there's some air resistance that's going on as well. Then this changes a little bit. Remember that potential energy is only defined for conservative forces. So let's just write this, let's just specify that this is going to be, right, the work from conservative forces only. And the WEP, the work energy principle, it's not going to change at all. So we can express the net work done, say, in terms of both the work done by the conservative forces and the work done by the non-conservative forces. So, right, that would still be the net work done. NC means non-conservative forces. And then how does equation 2 change? Well, we already wrote up here that change in potential energy is going to be, right, minus W conservative. All right, now what happens when I take equation 1 plus equation 2? I'm going to have equation 1 plus equation 2, the work done by conservative forces is going to go away, but the work done by non-conservative forces is not going to go away. So on the right-hand side, instead of 0, I'm going to have the work done by non-conservative forces, right? And the same thing over here. And the same thing, right? I'm going to have a work done by non-conservative forces over here. Now, this is very interesting because what we have in this case, where there are non-conservative forces introduced into the system, is the change in kinetic energy plus the change in potential energy is going to be equal to the work done by those non-conservative forces. In other words, the non-conservative forces remove mechanical energy from the system. How much mechanical energy gets removed from the system? It's just the work done by non-conservative forces. So when I carry this through, you'll see then I have final kinetic plus final potential equals kinetic energy initial plus potential initial plus the work that's done by non-conservative forces. So in the case, say, earlier, where, remember, I had a backpack and it was going to slide down a ramp, and I had used conservation of energy to determine the speed at the bottom. So just to remind you, when mu was 0, right, I could do 1/2 mv final squared equals, I set the potential energy, my reference point, to be 0 here at the bottom, and it was mgh up here at the top. So I could write 1/2 mv final squared equals, the initial kinetic energy was 0, the final potential energy was 0, so it was just 1/2 mv final squared equals mgh, the initial potential energy. In this case, where I have a non-zero friction force, I would have kinetic energy final is the initial potential energy, mgh, plus the work done by non-conservative forces. Now, how much work is going to be done by non-conservative forces as this backpack slides down the ramp? Well, it's going to be a negative number, right? Because the displacement is going to go down the ramp. Friction is going to act up the ramp, right? Because friction always resists motion. So, in other words, I'm going to have that mgh and then a negative number here. So my final speed then is going to go down because the friction force, which is non-conservative, removed some of the energy from the system. Now, this is then a general framework where you can still use this setup, this energy setup, to solve problems, even in the case where it's not all conservative forces that are acting on a system. So this is a very important thing to understand. It's an important concept that all forces are either conservative or non-conservative. If they are conservative, they completely conserve all of the energy, so mechanical energy will be the same. If they're non-conservative, then they're completely removing energy. So all of the work that the non-conservative forces do remove energy from the system. And they convert it into internal kinds of energy. It's not that energy is really created or destroyed. It's that mechanical energy gets destroyed because it gets converted into some kind of internal energy, like heat or sound, say, gets lost from the system. So that's exactly what's happening when the non-conservative forces do work.
All right, let's do an example problem, and I'm going to try to make this quick so that the video is not too long. So first of all, some strategy. So sometimes the work energy principle is the easiest way to solve a problem, especially when there's just one object and there's a net force acting on an object. You can use the WEP. Sometimes energy conservation is easier, right? And then when there are non-conservative forces, make sure that you include this term there. And don't forget that the non-conservative forces will remove energy from your system. So here's kind of a strategy for these problems. You should first draw a picture and then determine exactly what your system is going to be. Oftentimes, here the system is going to be both the spring and the block. You're going to want to include both. And you're going to want to pay attention to what the initial and final positions are and make sure you apply those things consistently. Choose a reference frame. So for example, here we're going to choose a reference frame, the natural reference frame for this problem, which is going to be where x is 0 at the equilibrium position for the spring. That's kind of the helpful coordinates to use. When it comes to potential energy, it's very important that you explicitly choose a frame of reference where you figure out where your reference point is for potential energy. And then you determine whether mechanical energy is conserved or not. If it is conserved, you use this one. If it's not conserved, you use this one. And then finally, you can solve for whatever you're asked to find. So let's take a look at this problem. A block of mass m is attached to the end of a massless spring of spring constant k, and that's shown in the figure below. The mass is given an initial displacement x0 from equilibrium and an initial speed v0. Okay, so it has both. In part A, we're asked to ignore friction, use energy methods to find both the maximum speed and its maximum stretch from equilibrium. Okay, so it starts out, remember, with an initial displacement and an initial speed. We're going to find the maximum displacement and the maximum speed, and you definitely want to use conservation of energy for this. Well, we know, right, the total energy the initial mechanical energy, the kinetic energy that it has initially is 1/2 m times v0 squared, and the potential energy that it has is 1/2 k times x0 squared, right? Because we are told that it has an initial velocity and an initial displacement. So remember, I've chosen my coordinate systems where x equals 0 at the central location. Now, if I want to find the maximum speed will occur right here at x equals 0, right? That's where the block will be traveling the fastest. So I also know, so that will be at this location here, and I also know that the kinetic energy then here is going to be the only portion of the mechanical energy, right? The kinetic energy at the maximum, at the equilibrium point at x equals 0 is going to be equal to, right, the initial mechanical energy, because energy is conserved. What I have is 1/2 m times v max squared is equal to this thing that I have written here. So I can just do some algebra. I'll multiply both sides of this by 2, and I will divide by the mass. And I can just take the square root of both sides then to get that v max is equal to root v0 squared plus k over m x0 squared. So that's my maximum speed. Not too bad. Now, we are also asked to find the maximum stretch from equilibrium. At the maximum stretch from equilibrium, right, there, we will have a velocity of 0 at, say, x max. We'll have velocity 0. So then my mechanical energy will be entirely made up of elastic potential energy. So KE final here will be 0, and the elastic potential energy at the final location is going to be 1/2 kx max squared. Then I have, from conservation of energy, that this 1/2 kx max squared is going to be equal to the initial mechanical energy. Now I can do some algebra again, multiply by 2, divide by k, and take the square root of both sides, and I have that x max is equal to the square root of x0 squared plus m over k v0 squared, and that is my final answer. See, not too bad at all. Now in part B, we're going to include friction. It says treat the path as being frictionless far from the equilibrium position, but as having a rough patch of width x0/5 centered around x equals 0, where it has a coefficient of kinetic friction μ0. Find the number of oscillations the block will go through before it runs out of energy. Give your answer in terms of the given quantities, μ0, as well as the original x0, v0, k, and m. All right, so here it's saying, right, we have a rough patch here. And outside here, we have mu equals 0, mu equals 0. But in the middle there, this has mu 0. It has a friction component. Now we're going to have to use, right, this version of conservation of energy, where we include the work that is done by non-conservative forces. So let's do that. Here, right, we're going to have the change in mechanical energy, right, or K final plus U final minus K initial minus U initial is going to be equal to the work that is done by non-conservative forces. And we're going to find the number of oscillations on the block will go through before it runs out of energy. Well, if this is the change in mechanical energy, what we can do is say, if we can find the work done by non-conservative forces in each oscillation, then we can take the total work done by non-conservative forces equal to n, say that's the number of oscillations, and we can say as soon as we have the work done by non-conservative forces equal to the total mechanical energy that it started out with, right, which was this there, then we have expended all of our energy and the block will stop moving. So let's see, what is the work done by non-conservative forces for, say, one oscillation? Well, the work done by friction in this case is going to be, well, it's a constant force, so work done by friction dot with the displacement. So as the object goes through, the displacement will be over this x0/5 is the width of that patch. So it will have a magnitude of x0/5. And notice that, right, when the object is moving this way, then the friction force, so if that's the displacement, then the friction force is acting this way, and vice versa. So F dot D is always going to be a negative number. They're always acting in the opposite direction. And that makes sense because we do want, it makes sense that the non-conservative forces are removing energy from the system. So we're going to have that this is equal to whatever the magnitude of the friction force is times x0/5, and that's going to be a negative number, right? Because they are anti-aligned with one another. And we know, right, that the work done by that the magnitude of the friction force is mu times the normal force. So we have minus μ0 times, well, the normal force when it's just when the plane is perfectly flat is just going to be m times g. So we have minus μ0 mg times x0/5, right, the distance. So that's the work that is done by non-conservative forces for one oscillation. The work done by non-conservative forces over n oscillations then would just be n times this exact number, minus μ0 mg x0/5. Okay, so this is the work done by non-conservative forces over n oscillations. Now, I want my change in mechanical energy to be, well, the final mechanical energy is going to be 0 because we wanted our final point to be when all of the energy has gone. And the initial mechanical energy is just this thing that we had started with over here, right? So we have minus this initial mechanical energy is going to be equal to the work done by non-conservative forces after n oscillations, or in other words, it's equal to minus mu naught mg x0 over 5 times n. And I can do then some math on this. So I will multiply by minus 1 on both sides to get rid of that, and then I can divide by mu0 mg x0 over 5, and that will give me n. So let's just really quickly simplify this a little bit. I have that n is equal to 5 over 2 times quantity v0 squared over mu naught g x0 plus kx0 over mu naught mg. This is the total number of oscillations that this system will undergo before it has lost all of its initial energy that was given to it. So I hope that was helpful for you. Good luck on all of your conservation energy problems.